This video is part of a series in which we present the design of an 8-bit microcontroller core called the EveCore. In this video, we'll present a short example program written in the EveCore assembly language. We'll walk through the instructions to show how the program works in order to give you a feel for the EveCore and its assembly language. In other videos in this series, we describe the EveCore architecture in detail, and there are also a number of videos showing how to implement this core in System Verilog. Here's our example program. If you are used to programming in assembly, this may look a little bit unusual, but it's not that different. Like any assembler, there's a single instruction on each line. In this example, we have several assembler directives. .flash indicates that this code will go into the flash memory. And we also see a string constant here. And then down here we equate some symbols with some values. So let's begin here at the top. This program is going to echo characters on the UART, and it's also going to begin by printing a message. So the first instruction is an example of the load SP instruction. Stack is going to grow down from high memory, so this is the appropriate initialization for the SP register. Then we see an example of the add 16 instruction, where we're moving a 16-bit address into the XY register. That's the address of this string down here that we're going to be printing. And then we call the print subroutine, and after it returns, we have this little loop. The loop has an in instruction here and an out instruction, and that's just going to read a byte from the UART and echo it back out. The UART receive symbol is defined at the bottom here, and that is the register that we query for receiving a byte. And likewise, UART transmit is the address of a register we can write to in order to transmit a byte. So here we are echoing the character. Next, we see a move immediate instruction. So we're moving the ASCII code for the Q character into B, and we're then comparing the values in A and B. And if they are equal, we go to main and print the message again. And otherwise, we have an unconditional branch instruction, and we go back to loop. So we just keep echoing characters until the user types a Q. The string directive is used for just placing characters in flash memory or RAM memory. We are only using the flash memory in this example, but there's also a .ram assembler directive, so we can lay out the bytes in RAM. We can't put instructions into the RAM or anything, but we can at least define where variables are going to be in the RAM. Here's a print function. And we see some code here, and it ends with a return instruction. We're using the load code instruction to go to the flash memory at the address in the XY register, fetch a byte, and then subsequently we are sending it to the output here and then looping back for the next byte. We use the add 16 instruction here to increment the XY register. This is a move immediate instruction and a compare instruction, and then we have a conditional branch instruction, and then down here we have an unconditional branch instruction. So even though this assembly code looks a little bit different than you might be used to, it is really pretty basically assembly code, and hopefully it's a bit more readable, and a beginning programmer can sort of understand what this program is doing just by reading the instructions. Now let's go ahead and run our simple example program and see what happens. First, we need to assemble it. I've opened up a command line shell window here, and the command that we need is this one right here. This invokes the assembler that I wrote, and the input is a file that contains our source code assembly language. And the output file is specified here, romdata.hex. So we can go ahead and run that command, and if there had been errors in our source, they would have been printed here, but there were none. So now let's take a look at what is in this romdata file, and we see that it's just a bunch of bytes that are not particularly meaningful to us humans. These are the bytes that will be used when we run the Lattice IceCube 2 software to build our FPGA. It will go to this file and collect these bytes and use them to initialize the block RAM memory. But in order to see exactly what the assembler is doing, we can also use this assembler to produce something that's in the so-called listing format. So with this command, again invoking the assembler on the same input file, but now using the -L for listing, and we're also going to specify a different output file. When we run this, it produces a file, and if we take a look at what's in that file, we see this. And what do we see? Well, on the left-hand side, the assembler is printing out the addresses, and then here it's showing the bytes that are going into those addresses. So we see, for example, the call instruction right here went into address 6, and it had an opcode of C3 and an immediate address of 0033. And we see that other instructions, for example, take only 1 or 2 bytes. Now, if we scroll down to, say, 0033, okay, let me go back up a little bit here. We see that at 0033 is the first instruction of this print subroutine. Also, I should note, at the bottom of this file, the listing includes information about how many bytes it actually produced. Okay, now I've already flashed the FPGA and we are ready to run it. I've got a little terminal emulator program, and that's shown right here. This program is called CoolTerm, and it works both on the Mac and on Windows. On Windows, a lot of people also like to use TerraTerm, which is a similar kind of terminal emulator program. And basically, what we're going to do is connect this program to the FPGA, and it will communicate over the USB cable. So when our code prints to the UART, it will go through the USB cable, and the characters will be displayed in this window here. So now I'm going to go ahead and reset the FPGA by pressing these left 2 buttons here. And that raises the reset line and causes the reset. And we see that it prints out our greeting message. And now I can type, for example, A, B, C, and it echoes just as we would expect. And then when I hit the Q character, like this, it just loops back and prints the greeting message again. And so it looks like our program works just as we expect it to. Well, that wraps up the demo. If you want to learn more about the EveCore project, you can consult the website shown on the screen. In any case, thanks for watching. I will see you in the next video.